Welcome to this video on how neural networks work, layer by layer. I'm Mujib-ur-Rahman, and today we'll demystify the core of modern AI. Neural networks power systems like ChatGPT and self-driving cars, and understanding their structure is key to understanding artificial intelligence. AI is a broad field. Machine learning is a subset of AI, and deep learning is a subset of machine learning. Neural networks are the core technology behind deep learning. They are everywhere, from voice assistants to analyzing medical scans. A neural network is a system of connected nodes, or artificial neurons, inspired by the human brain. Learning happens by adjusting connections called weights. A synapse in the brain is equivalent to a weight in the network. Given enough data, they learn to recognize complex patterns. Neural networks are essential across multiple domains. They are the backbone of image recognition, power large language models for natural language processing, and guide recommendation systems. They also drive innovation in healthcare AI and game playing, such as AlphaGo. A neural network acts like a data processing pipeline with three main types of layers. The input layer receives raw data, hidden layers process features, and the output layer produces the final prediction. Networks with many hidden layers are known as deep learning models. The input layer is the entry point, receiving raw data. Each input neuron represents one feature of the data, such as a pixel's brightness in an image. It does not process data, it simply passes it to the next layer. The number of input neurons equals the number of features in your data. Hidden layers are the network's brain, responsible for extracting complex features. Earlier layers detect simple elements like edges. Deeper layers combine these to recognize complex shapes and objects. More hidden layers allow the network to learn increasingly intricate patterns. The output layer delivers the final answer. The number of neurons here depends on the task. Binary classification needs one neuron, while multi-class tasks need one neuron per class. Activation functions convert the final values into usable probabilities or continuous outputs, like a price. A neuron is the fundamental building block. It receives inputs, each scaled by an adjustable weight, adds a bias value, sums them up, and then uses an activation function to decide its output. This simple calculation, repeated across millions of interconnected neurons, generates intelligence. The neuron works in 5 steps. Receive inputs, multiply them by their weights, calculate the weighted sum, add the bias, and finally, apply the activation function. This mathematical process transforms the input values into a single, usable output for the next layer. Activation functions introduce nonlinearity, enabling the network to learn complex patterns. ReLU is standard for hidden layers. Sigmoid is used for binary output, squishing values between 0 and 1. Softmax converts multiple outputs into probabilities that sum to 1, ideal for multi-class tasks. Forward propagation is the process of data moving directly from the input to the output layer. At each layer, every neuron computes its weighted sum plus bias, followed by activation. This single pass generates the network's prediction based on its current set of weights. No learning occurs at this state. The loss function measures the error between the network's prediction and the true reality. Low loss means an accurate prediction, while high loss indicates a significant error. The primary goal during training is to continuously minimize this loss over time. MSE and cross-entropy are common loss functions. Backpropagation is how the network learns. After measuring the loss, the network travels backward to figure out which weights contributed most to the error. Using gradient descent, it adjusts these weights slightly to reduce future loss. The learning loop repeats thousands of times until the loss is minimal. Training is the repetitive teaching of the network using labeled data. An epoch is one full pass through the entire dataset. Training often uses batches, which are small groups of samples for each weight update. The learning rate dictates the step size for these adjustments, ensuring steady progress and preventing overfitting. Let's trace a simple example, identifying a cat. The input pixels are refed forward. Hidden layers first detect edges, then combine them to recognize features like ears and whiskers. The output layer gives a high probability for a cat, resulting in very low loss, demonstrating a successful classification. Neural networks offer many advantages. They learn complex, nonlinear patterns and improve as they receive more quality data. They are adaptable across various domains, and their design allows for efficient parallel processing on GPUs, leading to blazing speed. However, neural networks face limitations. They require massive amounts of labeled data and significant computational resources. Challenges include overfitting, the black box problem, where decisions are hard to explain, and ensuring the model is fair by avoiding bias in training data. Neural networks drive numerous real-world applications. They power AI assistants like ChatGPT, enable self-driving cars to navigate, assist in medical diagnosis, and perform face recognition. They also facilitate language translation, generative art, and complex financial analysis. To summarize, neural networks mimic the brain using layers of neurons. Data flows forward. Each neuron performs a weighted calculation, and the network learns by minimizing loss using backpropagation. These powerful concepts are the foundation of modern AI applications across the globe.